Hello, class. I wanted to do this video. This is a review video for the midterm and help you prepare for the midterm. Did a review session, and many of you were unable to attend the review session, and I was unable to record that session. And so, what I'm going to do is go through a few things just to point out and to help you prepare for the midterm, which is coming up for week 4. The midterm will cover weeks 1, 2, 3, and 4, and then the final will cover weeks 5, 6, 7, and 8. And so, the best way, or one of the best ways to prepare for this midterm as well as the final, is the resources. Each week, you're given resources. This is the week 1 resources. And what I want to do is just go through a few of these just to help you get acclimated to the information that is provided for you and that will be helpful to prepare for the exams that are coming up. So let's look at this first one. For week 1, you did significant figures, you did conversion factors, and you did the mole. And so that will be chapters 1 and 2. So I wanted to go through a few things for this first one. We're looking at significant figures. And for significant figures, there are certainties and measurements. These are the rules for significant figures. I want to make sure that you're understanding the rules very well. So when we're looking at digits 1 through 9, they're always significant. The problem comes in, or the changes come in, when we add zeros. And so a zero that's between two non-zero numbers, that would be significant. And it doesn't matter how many zeros are in between two non-zero numbers, they're always going to be significant. And then there's certain zeros that are called placeholders. These placeholders have a importance in telling us what kind of number we have or how large or small the number is, but they are not significant. So the zeros in front do not count. We're looking at the 2, the 4, and the 4. There's only 3 significant figures here. Zeros at the end of a number, as long as there is a decimal present, they are significant. And so this decimal makes those 2 zeros at the end significant, giving us 5 significant figures there. But if their zeros are there and there's no decimal, then those would be considered placeholders and they would not be significant. The decimal makes those significant. All right. And so here's some examples. Let's go through these. So 4,500 liters. These 2 zeros are not significant because there's no decimal present. So there's only 2 significant figures. If we look at this number, 0.00607000, these 3 zeros are significant because of the decimal, but these 3 zeros in the front are not significant because they are placeholders. The 0 in the middle is in between the 6 and the 7. So they are significant. So we have 3 here and 3 here, giving us 6 significant figures. 400,000, because that decimal is there, it makes all of these zeros significant. Note that in chemistry, you can put a decimal here, but you don't have to put a 0 after that. That decimal simply tells us that all of those zeros are significant. So we have 6 significant figures there. 0.00543, we have the 5, the 4, and the 3, so only 3 significant figures. 500,003, because all these zeros are in between 5 and 3, it makes them significant, so 6. And this number, 500340035.000. Okay, that's a lot of numbers. All these zeros in here are in between non-zero numbers, so they're significant. These zeros back here are significant because of the decimal. So that means we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 significant figures. Okay, so that's to give you a little overview of significant figures. So we're going to go back now. All right. So hopefully you're still seeing what I'm seeing. So now we want to look at just a few brief calculations with our significant figures. So with addition, I want to point out that for the rules for adding or subtracting, you're going to look at the number of decimal places, or in other words, the amount of numbers after the decimal. We're going to go with the least to tell us how to round our answer. So for 52.09 minus 49.7, we have 2.39. Because this number only has one decimal place, our answer should only have one. So we're going to round this to 2.4. All right, so now we're going to look at division. For division, as well as for multiplication, you are looking at the least number of significant figures, so our answer should have that least amount of significant figures. And so we have this number 5.0033 divided by 5.0. So if we put that in the calculator, 5.0033 divided by 5.0, we're going to get 1.00066. But this number has five significant figures. This number has two. We want to go with the least, and so we're going to round our answer to 1.0. Okay, and that's grams per milliliter. So that would give us the two significant figures that we want for our final answer. Okay, so remember, adding and subtracting, we're going with decimal places. Multiplying and dividing, we go with the least number of significant figures. All right. And so the last thing I want to look at is the mole calculation. All right. And so we're looking at the mole. All right. So the mole has two definitions, or two ways we can define the mole. One is relating the mole to the number of atoms or the number of molecules, and that can simply be done by relating it to Avogadro's number, which is 6.02 times 10 to the 23rd. We use atoms if we're talking about elements. We use molecules if we are talking about compounds. And so the other thing we can relate the mole to is the number of grams. And this number can be found in your periodic table. It's the bottom number listed for each element. So for carbon, 1 mole of carbon is 12.01 grams of carbon. 1 mole of argon would be 39.94. These numbers, remember, come from the periodic table. We can use this to either go from moles to grams, or to go from grams to moles, or you can change to atoms or molecules. And so if we start out with this problem, what is the mass of 0.0500 moles of magnesium? We would start with 0.0500 moles of magnesium times 24.30 grams of magnesium over 1 mole of magnesium. We're going to multiply the two numbers that are on top. We would divide whatever's on the bottom of your conversion factor. Because what's on the bottom is 1, it's going to give us the same number. And so we get 1.22 grams of magnesium. Now, to determine the number of significant figures, remember we're always going with the least when we're talking about multiplication and division. However, this 1 mole, we do not use that to determine the significant figures. We're only going to use these two numbers here. So 0.0500 would have three significant figures. 24.30 would have four. Remember, we're going with the least, so we get 1.22 grams of magnesium. When you're setting up this problem, one thing I do want to mention, whatever you're starting with, you'll be given in the problem. So you start with that. And then whatever units you start with, that unit goes to the bottom of your conversion factor. So moles are what we start with, moles go to the bottom, grams are on the top. And remember, this number comes from the periodic table. All right. So if we start off with grams and we want to go to moles, then we use the same method. We're given 5.00 grams, so we're going to start with that. AU is the symbol for gold. We're going to multiply it by 1 mole of gold over 196.97 grams of gold. That number, remember, comes from the periodic table. Now, instead of multiplying by our grams, we're dividing because they are on the bottom. We get 0.0254 moles of gold. We started off with 5.00, which has 3 significant figures. 196.97 has 5 significant figures. We go with the least, so we will have 3. Okay. All right. So now we could go from atoms to moles and then moles to grams. Okay. This is a two-step problem. So it says an experiment calls for 3.75 times 10 to the 23rd atoms of calcium. We want to know how many grams are needed. So we start with 3.75 times 10 to the 23rd atoms. Okay, that's given. So that's what we're going to start with. We start with atoms, so we want atoms to go at the bottom. Remember, this is Avogadro's number. 1 mole over 6.02 times 10 to the 23rd atoms of calcium. Both of these numbers have 3 significant figures, because if we're looking at significant figures for numbers that are in scientific notation, all the numbers before the X or that times symbol are significant. So there's 3 here, there's 3 here, so they're both the same. So 0.623 moles of calcium giving us 3 sig figs. We start with this now, and we want to go to grams. This number, remember, comes from the periodic table, 40.08 grams of calcium over 1 mole of calcium. We get 24.9698, but we have to round that to 3 significant figures, 25.0 grams of calcium. Okay, so this is just to give you a heads up of how to do these calculations. There are examples here where you can actually practice on your own before clicking to reveal the answer. I would strongly suggest going back through each of these weeks as I'm going through just a few examples, just to give you a heads up of how to use this information or these resources to your advantage. All right, so we're going to go back to the main page. All right, and we're going to go to week 2. Let me close that up. Maybe close that up. Okay, there we go. All right, so we're going to go to week 2 now and go through the week 2 resources. Okay, so for week 2, we looked at naming binary compounds. We looked at formula weight, molecular weight, and molar mass. We looked at the nomenclature guide. We looked at polar, covalent, shape, and polarity. Okay, and this was our lab assignment that we worked on for that week. Okay, we dealt with shape, polarity, covalent bonds, and so forth. But I want to go through this particular one. And if you have questions on any of the other sections, please let me know. But I wanted to go through the calculations for this particular chapter or this particular week. So we go to the formula weight. There are two topics for this particular week: formula weight and molecular weight. They are the same as far as how to determine the value. Okay, the one thing that does change for these two terms are the units. Okay, and so for formula weight, the units are AMU. AMU stands for atomic mass unit. And so to determine the formula weight, for example, sodium chloride, we look at the mass of sodium, and that can be found in your periodic table, and the mass of chlorine, also in your periodic table, and we add them up. So 22.99 plus 35.45 gives you 58.44. That is how you find the formula weight. The units are going to be AMUs. To find the molar mass, it is the same. The only difference is that you have 1 mole of sodium chloride is 58.44 grams of sodium chloride. And so the only difference is the units, okay? The same thing with copper 1 nitrate, okay, which is CuNO3. When you have a particular example where you have more than one atom of that particular element, like for example here we have a subscript of 3 that tells us we have 3 atoms of oxygen. For the example we did before, we take the masses and add them up. We still take the masses and add them up. The difference is we have to multiply the mass of oxygen times 3 first before we can add them all up. Once we have the mass for a particular compound, just like we did for week 1, we can go from grams to moles or moles to grams using the mass for the entire compound. So in this example, we have 515 grams of sodium chloride times 1 mole of sodium chloride over 58.44 grams of sodium chloride. We're going to divide these two numbers. We get 8.81 moles of sodium chloride. Remember, you're not using the 1 to determine the significant figures. All right, I wanted to get to think there's an example. Yes, thank you. All right, so I wanted to get to this example where we're looking at the formula weight for a particular compound that has more than one of a particular element, like this example for H2O. We have 2 hydrogen and 1 oxygen. So, just like I said verbally, I wanted you to see this visually. You're going to take 2 times the mass of hydrogen, 2 times 1.01, and then you're going to add it to 16. That's how we get the 18.02. Okay. All right. So I did want to show you that. All right. So the other two to give you some practice. Okay. So now you see the steps that we go through to get to these values. This will give you some practice so that you can see for yourself. Okay. And then, like I said, the nomenclature, the polar bonds, the shape, and the polarity. I looked over your labs and you guys did an awesome job with that. And so, if you have questions, though, let me know concerning those topics. So, now we want to look at week 3. Okay. So, here for week 3, maybe we'll go to week 3. It's having a struggle. Okay, here we go. All right, week 3 resources. All right, so with week 3, we did calculating the yield of the reaction. We did free energy and reaction rate, chemical equations, the mole and mass relationships in a reaction, reactions involving water, concentration and dilution, gas laws, precipitation reactions. So we did quite a bit for this particular week. And so I want to go through a few of these just to give you a heads up and to show you some examples. I know we're still in week 3 until Monday, and so hopefully this will help you as you're going through week 3. But I want to go through calculating yield of reaction. So we determining the limiting reaction, theoretical yield, and percent yield. And so when we're looking at the limiting reactant, we have two particular reactants. And so the reactants are going to be here on the left side of the arrow. The products are on the right side. So there's going to be one reactant that's limiting. There's going to be one reactant that is in excess. Okay, and that's true for your different reactions. And so the one that's limiting limits the amount of product that we can produce. And so to do this, it says if 2.10 moles of N2 and 5.70 moles of H2 are used in the reaction, which is limiting. So let's look at how we would set that up. So we would take the 2.10 moles of N2, just simply because it's listed first, and we want to convert it to moles of H2. So 2.10 moles of N2 times 3 moles of H2 over 1 mole of N2. So where did we get the 3 and the 1? That came from the coefficients, or the numbers in front of the substances in the balanced chemical equation. You see that there's no number written for N2, then that means it's understood to be 1. And so that's where we get the 3 moles of H2, the 1 mole of N2. The 3 and the 1 we do not use for significant figures. Just like before I mentioned we didn't use the 1, these are called exact numbers because they actually count something. And so we don't use those for significant figures. We are going to use the 2.10, which is 3. So we get 6.30 moles of H2. So if 6.30 moles of H2 are needed, but you have 5.70 moles of H2, that means that H2 is the limiting reactant. Okay, so that's how you determine that. All right, so you can go through um, these examples. All right, but I do want to get to an example of theoretical yield. It says, what is the theoretical yield of CO2 in moles and grams if 2.2 moles of propane react with 14 moles of O2? So in order to determine the theoretical yield, you must first determine the limiting reactant. And so, just like we did before, we're going to start with 2.2 moles of propane. Propane is C3H8, okay? Excuse me. And you want to convert that to moles of O2. And so we're going to again use our coefficients, the numbers that are in front of the substances. Remember again, if there's no number written, it's understood to be 1. So we have 5 moles of O2 over 1 mole of C3H8, which is propane. We get 11 moles of O2. Because the 2.2 moles only produces 11 moles of oxygen and we have 14 moles of oxygen, that tells us that the propane is the limiting reactant. When you're determining the theoretical yield, you are going to use the limiting reactant to determine it, okay, since that limits how much product we can produce. So 2.2 moles of C3H8 times 3 moles of CO2 over 1 mole of C3H8, okay, because we're looking at the theoretical yield of CO2 and we're not looking at H2O. We get 6.6 moles of CO2. So we wanted to know the moles of CO2. We also want to know the grams. So we're going to take the 6.6 moles of CO2. We're going to multiply it by its molar mass, 44.01 grams CO2 over 1 mole of CO2. You get 290 grams of CO2. If we look at 290 grams, 6.6 is two significant figures. 290, that 0, because there's no decimal present, The 290 is two significant figures, and so you have the correct number of significant figures. All right, so let's look at what else we can find. All right, so we have free energy and reaction rate. So I want to look at that with you. All right, okay. I wanted to see if there was a calculation, but no, it's just the graph in terms. Okay, here we go. This is what I wanted to go through. Okay, so this is giving you another example of theoretical yield. All right, so as you go through that, that's basically information that if you have questions about it, let me know. But I wanted to go through more of calculations. And so let's get to concentration and dilution and then the gas laws. Okay. All right, so for concentration and dilution, all right, so there are some calculations here. And so we have weight, volume percent, and weight percent. And these are the equations that are associated with it. So whatever's on top, like if weight is on top, it would be the grams of the solute. If volume is on top, it would be the milliliters of solute. And then the bottom is always going to represent your solution, whether it be milliliters or grams. And we're always going to multiply by 100. Since 100 is part of the equation, we do not use this for significant figures. So keep that in mind. All right, so let's look at a weight percent problem. WW stands for weight, and then the percent. So we have a sample of 0.892 grams of KCl is dissolved in 54.6 grams of water. And so we want to know the weight percent of KCl. So we have the weight of the solute. To determine which one of these substances is the solute, if you're looking at a solution that has water, water is always going to be the solvent. And so whatever is being dissolved in the water is known as the solute. Another way you can determine which one is the solute is the one that's in the smaller amount. And so again, KCl applies to that rule as well because it's in the smaller amount. And so that number is going to go on top, 0.892 grams of KCl. Remember, the bottom is the solution. So the solution is not only KCl, but also water. So we have 54.6 grams of water plus 0.892 grams of KCl. Remember, for significant figures, for when we are adding, you go by decimal places. So since this only has one decimal place, your answer at the bottom when you add these two numbers should only have one decimal place. So when we take this number divided by the addition here, then we're going to multiply it by 100. You get 1.61% because we needed three significant figures here. So that'll give you an example of that. And then there's parts per thousand, parts per million, parts per billion. The difference here is what we're multiplying by. Since we're not talking about percentages, we're going to multiply this by 1,000, this by 1,000,000, and this by 1,000,000,000. Okay. All right, and these are just some examples of that. But what I want to get to is molarity. Molarity is equal to moles of solute divided by your liters of solution. And so in this particular example, it says, what is the molarity of a 2.50 liter sulfuric acid solution containing 1.26 moles of sulfuric acid, H2SO4? So we have our moles. 1.26 moles over 2.50 liters, and we get 0.504 molar. Okay? And it sees that my time for this video is about to end, and so I'll come back with a part 2 video.